clear factor. Okay, clear factor is the small area. This green area. Okay, this green area divided by blue area. Okay, this is clear factor. Okay, big square, small square. Okay, so this is the small square versus big square. Okay. Not this area, okay? Not this area. Big area, okay? Okay? So, absorption and conduction. Here, we need some parameter that we need to minimize, so-called reflection. Reflection, we need to minimize. Minimize the reflection, that means on the surface of the cell, if there is light, reflect. So which means that less light being absorbed to the cell, right? So therefore, we have to, as possible as we can, to absorb the light, to make the surface can so-called light penetration or light scattering. Okay, if the light is just reflect, and then there's a less light being absorbed to the materials. So therefore, we have to minimize reflection. Okay. And also minimize the recombination. Okay, recombination. The recombination, we will always have many cases to talk about recombination. Recombination, that means when the materials has been generated the photon current or photon excited electron, we call the charge. Okay. Last chapter, we have talked about the valence and conduction band, right? So here is the Eg. So if the light energy, if the light is large, we call it Eg. So the electron will be excited to here. Okay. Excited to here. And when the electron drop to here, we call it recombination. This is the which means that the electron, the charge has been separated but being recombined to something, right? Some defect, for example. Okay, so we need to minimize. And mass of course, mass absorption. Okay, mass absorption. So mass absorption, that means for the material side, you need to create a large wire band gap absorption, right? Wire band gap absorption. And also, if we can do something else to create some higher surface properties, okay, and then this line could be scattering on the surface and highly absorbed to the materials. So therefore, the line has more pass. Okay, has more pass through, more pass to absorb to the materials and create high efficiency. And also conduction. Okay, conduction doesn't mean the carrier can move in the materials which has higher conductivity, for example. So accordingly, we have for the silicon solar cell, we have three types. One is amorphous, polycrystal, and single crystal. So, you know, for the polycrystal, single crystal, and amorphous, there's a significant difference. For the carrier transfer in amorphous, it's a more hot, right? Because there is no consecutive layers. So therefore the electron has a lot of the barrier. But for the polycrystal, there's some single crystal, but still there's a grand boundary. Okay, there's a grand boundary. So those grand boundary act a barrier. So the electron must overcome this grand boundary in order to transfer to another brane. But for the single crystal, it has a high mobility. In the perfect single crystal, there's no defect, there's no standing fault involved. So therefore, the electron transfer should be fast. So why we need the silicon? That's I always emphasize. It's abundant, okay, and cheaper. And silicon dioxide is very stable, so it is easy to find by SEM. Okay, strong dielectric, easy to grow by thermal process. Okay, and then data is 1.1. So just allocate, and when the wavelength is reachable light, right? So is our best friend. Operation temperature is also quite high, quite wide, right? So it is good materials for the solar cell, okay? And then this is the Yin-Hand diagram, okay? Thermodynamical Yin-Hand diagram. The Yin-Hand diagram, I think you guys should be able to know about the free energy, okay? The free energy. If we look about the free energy as a function of the curve, the temperature, silicon dioxide is right here, okay? So free energy is a negative value, which means very stable, very stable. It's quite stable. So we can use some of the carbon, right? We can use the carbon to produce the silicon with CO2, right? CO2. So you can purify the silicon. So this is based on the price. If you look about the polycrystal silicon, okay, to produce the ink-gun and then become the wafer, and then for the transistor use, okay, wafers, you can see the price is increased. Okay, the price is increased. So from here to here, okay, from here to here, it is a lot of the process we have to apply. Okay. For example, although the single crystal manufacturing process later we will show about the single crystal manufacturing process. Polycrystal is still one of the very famous process for the company, okay, manufacturing company. They would like to use the polycrystal because polycrystal much cheaper than single crystal. And then the important case is how to purify the grain boundary area, the metal transition in the grain boundary area. This is very important. So if we can produce a high purity polycrystal, okay, high purity polycrystal, so-called in the grain boundary area there is many defects. We can minimize the defect, and then could be another solution to produce the cheaper solar cell in contrast to the monocrystal silicon. Okay. So process is quite important. Okay. And next, I wanted to show you about the single crystal silicon and polycrystal silicon. There's a Tchaikovsky process. Okay. Let's see about the Tchaikovsky process. There's a video. One moment, I'll show you the video. Before to talk about the Tchaikovsky process, here is the video, okay? The size the size of the Tchaikovsky will look like that. Okay, it looks like you have ceramic support connect income. Okay, this is the seed. Okay, and then inside you have the crucible, and there is a molten state of the silicon. Okay, and this is the insulator ceramic. Okay, usually it's using graphite. Okay, it's using a graphite. Okay, and then it is the beige, okay, close. Okay, so you can see deep. Okay, the size will look like this is the engineer is right here, so it is quite huge. So you can see, for example, we have the quartz crucible, and then the molten silicon usually is 1,000, 14,000. Okay, over than 14,000. Increased to the over than 14,000, and then this is the heating coil, okay, and this is overall furnace. You can see this rotate to this way, rotate to this way, and there's an income here. Single crystal silicon seed rotate to another way. Okay. This is the opposite side. Okay, opposite side. So let's see about the video. This is quite interesting.
It all begins with a It all begins with the growth of pure silicon crystals. Silicon is the common element found in sand. It is 28% of the Earth's crust, and second only to oxygen in abundance. The silicon from the sand is refined and purified as polysilicon chunks. The purified silicon is then heated to a molten state. A small solid piece of single crystal called a seed is gently lowered into a rotating vat of molten silicon. Using the cubic atomic structure of the seed as a pattern, a new crystal will form as the symmetrical extension of the original seed. The hot liquid silicon in contact with the seed begins to cool and solidify as it is gently pulled from the molten region. The cubic atomic structure of silicon consists of atoms with 4 electrons in their outermost shell. In a perfect crystal and at low temperatures, each silicon atom bonds with its 4 neighbors. There are no free electrons to conduct current. At room temperature, however, the silicon crystal has enough thermal energy to free a small number of electrons. These free electrons conduct current, as do the holes where the electrons have been. This conductivity can be increased by adding impurities called dopants. Dopants are elements which are similar to silicon in atomic structure. There are 2 types of dopants. N-type dopants, like arsenic or phosphorus, have 1 more valence electron than silicon. P-type dopants, like boron, have one less. When some silicon atoms are replaced by arsenic or phosphorus, the crystal is called N-type due to the extra electrons or negatively charged free carriers. If boron is used, the missing electron behaves very much like a positive carrier. The crystal is called P-type. These free electrons and holes move through the crystal, conducting electrical current in response to applied electrical fields. After 48 hours of growth, a single crystal results from the liquid melt. The ability of silicon to be either a poor or a good conductor by fine control of dopant concentration makes silicon a member of a class of materials known as semiconductors. The shiny rippled surface of the crystal is ground to form smooth, uniform ingots. A curved diamond-edged blade saws the ingot into wafers that are as thin as possible without being too fragile and difficult to handle. The wafers are scrubbed and the edges are rounded off and beveled to reduce chipping. The wafers are then ground smooth on both sides to obtain a consistent flatness and thickness from wafer to wafer. They are rinsed and etched in chemicals to remove surface contamination. The final polish is done on only one side of the wafer. The characteristic mirror-like luster is free from scratches and contamination. The wafers are measured for resistivity, which is a function of dopant concentration. They are inspected, packaged, and sent to fabrication areas where they will be
Okay. This is a typical Tchaikovsky pooling process to produce the single crystal. So you can see there's a seed. Okay, there's a seed. So this seed determines which area or which plane. Okay, which plane that we want to grow. Okay, so based on thermodynamic stable, so if we provide, for example, this plane is 100, and it will grow symmetrically in 100 plane, because 100 plane provide mostly thermodynamic stable. Okay, so therefore it will follow the symmetrical growth by thermodynamic fabrication. phase process. So it is quite interesting right here. You can see the single crystal is grow, rotate to the, for example, to the right hand side, but the crucible actually still rotate, progressively rotate another side. So can you understand what I mean? Can you know why they rotate opposite? What reason they rotate? The growing process is quite slow. Okay, growing process is quite slow. In order to reach the diameter, okay, if we wanted to diameter, for example, 12 inch, 8 inch, 6 inch, it is difference. Growing process speed is the difference. But why the seed rotation and crucible rotation is different? Is there any reason? If you think about the doping, we have talked about the doping, right? We have talked about doping. This is just like a study, right? We want to mix in the atoms, for example, the extra atoms, like the boron, the extra atom of the phosphor. If we add to the molten state of the seed, we rotate to the different way. This is a mixing. Looks like you will get a uniform doping. Okay, it's because of the uniform doping. So therefore, we wanted to create the opposite rotation. Okay, because of the uniform doping. So this is the process you can see progressively that introduce the seed single crystal and then progressively touch to the molten state of the silicon and then pull out. Okay, so in the initial here and finally, mostly there's a lot of the defect. Okay, and also dislocation. So we have to cut bottom and lower side. Okay, to get the high purity. So this is a very useful popular Tchaikovsky. Most of the single crystal be produced 80% using Tchaikovsky process to produce a single crystal silicon. And another 15 to 20% using another process. Later I will show you, so-called flow law. Okay, later I will show you. So this is the most 80%. Okay, quite popular. And then there's a specific cutting edge, as you can see. If you look about P-type, you could see right this way, you have the edge cut. Okay, and then this is N-type of 111, for example, this edge, and N-type. Okay, you have this specific edge. So I think in the lab, mostly we use N-type, right? You have such wafer, looks like that. N-type 111. So this is just showing we can identify the specific plane of the silicon. And another process, flow zone. Okay, flow zone process is the most very simple. Because the Tchaikovsky process requires a huge furnace. Okay, you can see the furnace is quite huge. And for flow zone, it is quite simple. You just need a coil, okay, coil, a so-called inductor, okay. Sorry, I don't have the power.
can use my laptop.
Oh, okay, okay.
मुझे एक बार वो भेजना PPT.
Maybe next time I need to bring the power.
Wait, maybe.
Can I use the power? Yes, DOT. Okay. Usually my battery can suffer 3 hours. And now it's getting low. So the flow zone, we just require heating coil, okay, outside here. So as you can see, we just have to provide for the top side, okay, you can see here, it's a polycrystal silicon. It's a polycrystal ingot silicon. And bottom side actually is a seed, okay, it's a seed. So as you can see, like this top. And then here is a core. And then on the bottom side, single crystal silicon. So this single crystal silicon progressively lamp up. And then this coil increase the temperature heating to the molten state, to become a molten state, just only this area. So this C progressively touch to the molten state of the silicon, and then there's a solid and liquid interface, right? So it's also rotate in the opposite direction. Here rotate to this direction, this direction, and here rotate another direction, right? You can see this is the opposite, right? The opposite direction, right? So therefore you can pull down, okay, pull down. So finally you also, because here is a liquid state, right? So the liquid state atoms will progressively attach to the single crystal seed, and then grows. Okay, and then grows. So growth becomes when they pull away, okay, drop away from liquid state of the silicon, and then become solid, okay, which will be form a single crystal chunk, okay, ingot. So this is a case for the germanium, okay, for the germanium. In outside is a coil, and here is a liquid state, okay, it's a liquid state, as you can see. Okay, there's a rotate, so here is a liquid state, okay, it's a liquid state. So whenever you can put the polycrystal on the top or polycrystal on the bottom, it's also okay. Both sides are okay. So you can prepare. Looks like here is a single crystal, right? Single crystal, and pull down, pull down. And top first side is a polycrystal. So you can see you can prepare a single crystal germanium and single crystal silicon. Okay. So this is a more convenient, and the facility has require less expensive, okay, compared to the Tchaikovsky process. All right, so if we want to create a doping, okay, for example, because the flow process here is a molten state, right? So we can use some of the gas. For example, you wanted to create nitrogen doping. You want to create phosphor doping or boron doping. You can mix here and then just spread the gas to the molten state of the silicon, so you can create a doping. Okay, create a doping, and still you can create. It is quite uniform. Okay, it is quite uniform. Okay, so this is with the radio frequency field, both are partially emit. Okay, both sides partially emit. So the C is brought out, okay, brought out from the below to make contact with the drop of metal, okay, of a knit form at the tips of the poly rod. So here is the poly rod. So and then create the necking process, carry out to establish dislocation-free silicon, okay, before neck is allowed to increase the diameter to form the taper, okay, which describe desired diameter. So the desired diameter is depends on the rotation speed, okay. I mean the diameter. If the rotation speed is slow, the diameter becomes bigger. So it depends on what size you want. Okay, what size you want. So the molten node is moved along the polycrystal, okay, polycrystal line, and then the molten silicon solidifies into single crystal, and then simultaneously we can also making the materials purified. Okay. So this is also one of the solutions that we can produce a single crystal silicon. So this is almost about 50 to 20%. Okay, 50 to 20%. So after we finish the single crystal silicon, and then next is to produce the wafer. Okay, to produce the wafer. So we can cut the wafer, and for example, cutting the wafer, still we have to think about how to purify the silicon, because using this kind of the process still has impurity, maybe be doped to the materials. So we have to refine it. Okay, we have to refine it. So refining requires some of the process we call zone refining process. Okay, zone refining. this slide shows that, for example, we want to purify the germanium seed. Okay, this income. Okay, because inside maybe impurity, there is a lot of the impurity. Okay, and we could use the long refining. This is similar to the flow long. Just outside, we apply the coil. Okay, we apply the coil, IF coil, and then increase the IF coil, so we can scan to this way. So therefore, those impurity will be repaired. Okay, will be repaired. Those impurity we can say is like a solute. Okay, solute. So this solute will be repaired into the liquid state. Okay, and then to move to this way until the end. Okay, and then we can cut it. So therefore, we can repeat again and again. So finally, we can purify this income. Okay, we call this as zone refining. Okay, this is the heat is moved to the right hand side, so you can see slowly, and then the molten sea and the germanium from the rock recrystalline. Okay, recrystalline as the temperature drop. Okay, so we can get an ultra high purity of the crystal type silicon. Okay, so this is one of the process we can do. Okay, so as the heater is moved to the right hand side, the ultra purity of the germanium move to the left side, and then the impurity move in the opposite direction because the impurity move to the opposite direction. So this is one of the process we can do. It's using a similar flow long process to create high purity silicon. Okay. So this process usually, let's just talk about the usual process. Metallurgical, Mg is a metallurgical silicon, and then we have to purify. Purify, I just mentioned you can use the flow long process or the long refining process to purify. But another way is also we can use the Siemens process, Siemens method. Okay, the Siemens method is also one of the processes we can do to purify. Siemens process, you can see like this way. This is the Siemens process. Okay, looks like there's a chamber. Okay, and then you have this outside here is the quartz bench. Okay, and then we have the preheater. Here is the preheater, and then here is a feed through. Okay, so-called just like a seed. Okay, a seed, like a filament. Okay, like a filament, and then now we have to use the silicon SiHCl3. SiHCl3. So how to produce SiHCl3? You just need to do that polycrystal silicon, for example, 99% or 98%, and then you drop to the HCl. Okay, and you will produce the SiHCl3. So this is one of the silicon precursor. Okay, silicon being totally melt or dissolved. I would say not melt. Silicon will totally dissolve in the HCl3. So you have the precursor of the HCl3 and simultaneously produce the hydrogen. So this hydrogen we can collect for renewable use. But anyway, we want to do the precursor of SiHCl3. So this SiHCl3 will be float into this chamber. And this chamber, be careful, you can see right here is a thermal, is a preheater, right? And if we apply the heater, increase the temperature, you could see the silicon SiHCl3 will be dissociated, right? And then dissociate become the silicon vapor, okay, surrounding inside of the chamber, okay? So there is a filament. There is a filament here, filament. Because you have the silicon vapor, and this atom will be absorbed to the filament, and then become progressively to grow on the filament silicon. Okay, to the silicon, to the filament. So here is the silicon. Here is the silicon. But because this is not single crystal, and there's only silicon in thermal growth on the filament, okay, on the filament. So finally, you have the silicon, right? And then you still produce the byproduct of HCl. So you will grow like that, okay? And then finally we crush. We crush to get the ingot, okay? Again, this ingot may be 99.99%. And then we can redrop to the HCl to dissolve the ingot. So you have the 4N SiHCl. 4N purity SiHCl. So you reuse, okay? SiHCl, high purity SiHCl3, right? This is maybe 4N. And this precursor we inject to the chamber again and dissociate again to deposit on the filament again, right? So finally, we get high purity. Okay, we can get high purity silicon ingot. So we can reuse to purity, to production of the silicon with high purity till 6N. Okay, so this is one of the process we can use the silicon like to produce the polycrystal. This is only polycrystal, okay, only polycrystal, because this fragment freeze through here is a freeze through. Freeze through, that means from the outer side to inside of the chamber, so-called a freeze through, okay. And inside is the fragment. Fragment just looks like a, it's a 灯丝, okay, 灯丝 fragment. Okay? So any question? And let's finish to here and let's finish to here and then we'll see you next week.